Hey everyone, thank you so much for having me. As said, my name's Seth. I work at Google. I work on the developer relations team, actually the same team as Valentin, did the previous presentation here. Today I'm going to be talking about something a little bit less Google Cloud specific and more about the Go programming language itself. As many of you know, we're kind of in the middle of a pandemic, and during that, some people took on slightly different job responsibilities to try to get the pandemic under control. And I did the same. I didn't like change jobs or managers or anything, but I shifted focus away from my normal day-to-day activities and started working on a project called Exposure Notifications. If you're not familiar, Exposure Notifications is a joint effort between Google and Apple to help governments and public health authorities fight the pandemic through digital contact tracing using iOS and Android mobile devices. I won't go through the whole program, but in short, when a mobile device is in proximity to another mobile device, in other words, when two humans are in close proximity, they exchange random rotating identifiers via low energy Bluetooth. And when a user tests positive for COVID, they can opt to upload those random IDs to a central server. And then on some fixed interval, usually every night when you're connected to Wi-Fi and plugged in, other mobile devices download those keys from that centralized server and perform a local on-device match. If there's a match, it means that you came in contact with someone who has tested positive for COVID. There's a number of parameters that are set by the local health authorities, so this is a little bit of a simplification. If there is a match, this generates what we call an exposure notification, which is a pop-up on your iPhone or Android device that says, hey, Seth, we think you've been exposed. We don't know who exposed you because the server only ever has random IDs. We never have identifiable information. And you don't know who exposed you because you only just get a notification that says you've been exposed in some recent time period. So because of this design, it means that the server never knows which keys you have or how many matches have occurred, and the client does all of the matching, whether it's the iOS, iPhone, or an Android device. A lot of the work goes into the mobile client itself, right? The operating system, but I don't actually work on any of that. I work on the server side. And we've written two server components, both in Go, that leverage a serverless architecture. And I want to talk to you today through some of the challenges we experienced and some of the mistakes that we made in building a piece of infrastructure that services about 100 million users a day. So with that, let's go ahead and get started with everyone's favorite pop quiz. So I know it might be early for some of you or late in the day for some, but we're going to start with a quick pop quiz. What does the following Go code print at the end? And I know there's a little bit of a lag between what I'm saying and what I see in the YouTube channel. So feel free to drop the letter of what you think it is in the YouTube chat. I'll give everyone, about 10 seconds for an informal poll, and then we will reveal the answer. Cool. So this actually prints empty curly braces. How many people thought that it would print empty curly braces? And this makes sense if you actually read and understand the Go specification, but this was actually, we thought it was going to print out the first item there, error key with the value of oops. And the reason for this is that error is an interface in Go. And whenever an interface is marshaled in JSON, it marshals to its underlying type. The underlying type for error string, which is what errors.new and format.errorf generate, is a private type called error string that has no exported fields. And when a type in Go or struct has no exported fields, it encodes in JSON to the empty object. We found this unintuitive. It caused a production outage, and it caused us to not have observability into another outage where we couldn't quite figure out what was failing. We were getting an error back, and then the response body was just the empty string because of a very similar pattern to what you see here. This is a little bit of a simplification. So this is one of the first gotchas that we experienced using Go, and something that we've actually kind of written a little linter for using some grep and some regex to detect. Another area where we had a few challenges were particularly around internationalization. Now, I recognize that not all projects need internationalization. You might be targeting a particular audience that speaks a particular language, but in our case, COVID is unilaterally affecting every country. So we needed our server to be able to support multiple languages. So our user interfaces, as well as some APIs, are internationalized. You sometimes hear this called I-18N, which is I and then 18 letters, and then N, which is internationalization. In short, that means that our UI is translated into many different languages. There are RFCs defined by a number of consortiums that talk about internationalization and how browsers and how the web in general handles internationalization. For example, RFC 2616 defines this thing, a header called accept language. It defines the header and the canonical formats for those headers. In your browser, when you set your preferred language, you may not know this, every request that you make, every button that you click, every website that you visit, your browser is sending that header along with a request. So if you were to translate that to a curl command, your browser is always running curl-h accept-language : and then the canonical value for the language that you set. Now, if you're using a modern browser like Chrome or Firefox, you can actually set multiple languages. So the accept language header isn't a single value. It's actually a ordered list in the preference that you want to receive languages back. So for example, if you speak French, you may pick French as your primary language, but then you may pick German or English as your secondary language. And then the website gets that information and it decides, do I want to serve this in French if I have a French translation? Otherwise, I'll fall back to German because that's my next best translation, given the user's preference. All of this happens completely like out of the user's control. All you do is set your preference in your browser. On the code side of things, you then have to read that header and determine which language to serve the request or the response in. So this is kind of what this code might look like. Again, this is a little bit of a simplification, one, to fit on a slide, and two, because we're really trying to zoom in on specific things here, of an HTTP middleware that would parse that header and set a translator on the request context and then call the next chain in the HTTP handling request. So there's a few things that I want to point out here. The first is that the parse accept language function, as defined by the core language package, verifies that the inbound string, which came from the accept language header, is a valid RFC 2616 format. Match, again, which is built into the language matcher, panics if you give it an unknown language. So some of you may have already spotted the challenge here, which is that header is user-supplied information that verifies that the language matches a particular format, but then the matcher itself panics if the language is unknown. So that header is user-controlled data, which means we can't trust it. It specifically means that a user could craft a request with something that matched the RFC 2616 format that would then cause match to panic because it was not actually a legitimate language. Let's take a look at a more concrete example. If we zoom out and we focus on just the lines here that are still in color, if we pass in a language tag of EN-Z, this is a valid language tag according to RFC 2616. It will pass all regular expressions and validation. However, that is not actually a valid language. EN-US is, EN-BR is, but EN-ZZ is not a valid language tag. So when you give that to matcher.match, it panics. So if we zoom in again, we already know that the header is a user-controlled piece of data. I could run a curl command and set this header. I could set this value to anything. It's untrusted data coming from the user. So what this means is that without very careful handling, including a recover statement, an attacker can cause a denial of service attack on your system by passing in an accept language header that passes the RFC 2616 validation, but is not an actual language header. As you can imagine, the Explosion Notifications project is a target for attackers. And we did have this happen, which is how we identified the issue. We were able to quickly mitigate it, but we found this behavior incredibly surprising. There's currently an ongoing investigation on the Go programming language about the best way to fix this in the actual language package itself, as well as evangelizing this particular edge case as a thing that can happen. If you're using any of the internationalization tools in Go today, I would strongly recommend that you either guard against this code path with a recover statement or verify that you're not vulnerable to this particular attack by doing something like an allow list of languages instead of using the parse language match function. So moving on to the next thing that we encountered, the database SQL functionality works really well for small applications. But what we found is that in our particular architecture, it had a number of shortcomings. First, it's really difficult to observe. We saw earlier a talk about like open census and open telemetry. It's actually very challenging to inject that handler and observability code into the database SQL package itself. There are, open census wrappers and a number of other things you can do, but at the end of the day, you end up having to write a custom driver to interface with MySQL or Postgres, even though there's great ones out there, just so you can inject your own observability hooks. The second thing that is somewhat unique to our architecture, because we run on Google Cloud Run, is when Google Cloud Run kills your container, it first scales the CPU to 0, and then there's a garbage collection job where later it actually goes and deletes the container instance itself. Now, that garbage collection interval is proprietary. I can't discuss how long it is, but it's long enough that another request could come in and cause that CPU to scale back up to 1, at which point you were throttled and then you came back online. So it's the equivalent of you taking a Docker container, taking away all of its resources, waiting a few seconds, and then giving it its resources back. The Go language itself doesn't behave well under these circumstances, as particularly anything related to time. And a number of things, including the database SQL package, leverage basically a for loop that results in a race condition in the case that CPU is throttled to 0. And it looks a little bit like this. I've, again, kind of oversimplified to fit on the slide and to highlight the issue. But here you can see we have this for loop where we're going and we're doing some work and we're waiting for the work to stop. And then in the actual work itself, we eventually close some channel which propagates through. You could also do this with context or something else. But the idea here is that after some period of time, we want to cancel. In the case of the database SQL package, this is actually a health check that makes an outbound connection. The problem is whenever this process is in the background and it has no CPU, none of this runs, but time continues to click along. So anytime you're dealing with time and CPU throttling, this pattern doesn't work anymore. And CPU throttling to 0 is a very common pattern in serverless frameworks, whether that's Google Cloud Run or Lambda or Fargate. It's very common to scale the CPU to 0. So this is a shortcoming that we identified in the database SQL package, and we're working with the Go team to try to identify ways in which we can make this better given a CPU scale to 0. The next thing that we encountered is something that's not unique to this project. In fact, the community has talked about this many times. Consider the following code. You can think of this as another pop quiz if you'd like. I'll give everyone a little bit of time to respond in the chat. What does this code do if the API key is invalid? So we have this, valid API key call, which I haven't defined, but assume it works. What happens if the API key is invalid? What does this middleware do in that case? Feel free to drop your answers in the chat, and I'll give everyone a few seconds because I know there's a little bit of lag. So there's actually 3 correct answers here. The best answer is E as an elephant, it depends. But the key here is that there's no return statement after the http.error call. What that means is that you return a 403 unauthorized response to the client, but then that code path continues execution. It means we call database.lookup session and any other code that exists in this function body. So depending on the expectations of the code that occurs after this, you may panic with something like a null pointer exception because you expected the API key to exist, or worst case, you have returned a successful response with a 403 status code, which is very confusing to end users and very difficult to debug when you're looking at your logs to try to reproduce this issue. Another area that caused an outage for us was the HTTP default client and HTTP default transport. These are global variables defined by Go. Because they're global variables, they also share state and can easily be overridden by other packages. Any package that you import, always be securing your software supply chain, can easily modify this default client and default transport using an init function. Furthermore, the HTTP default client itself has no default timeout. This means that when you make a request to a server, if that server acknowledges the request but does not return a response, you've occupied an entire IO thread just waiting for that response. This can lead to a denial of service attack or just really poor performance. Speaking of HTTP, another area which is a little bit of folklore in the Go community is rendering JSON or HTML into a response writer. So if you're building a RESTful service or any type of web API with Go, you're going to be rendering some JSON or HTML back to the client. And in the Go documentation and in blogs on Medium and whatnot, you'll see this pattern. Again, simplifying a little bit for slides, but this general pattern. For JSON, you'll call JSON.newEncoder with W, which is the response writer. You'll encode I, which is the inbound interface, which is like a structure. And if that fails, return an error. And then for HTML, you'll do the same thing, but you'll use like templates.execute template instead. Now, this actually has a problem. If I, which is the interface that we are marshaling, is sufficiently large, we could begin writing a successful response to W and then fail. Maybe there's a cycle in our JSON encoding, or maybe our template execution fails. If that happens, you have already sent a partial response to the client. You can no longer change the status code because HTTP requires that that's the first thing that you send before you send any body. And you can no longer change the structure because you've already sent partially valid JSON. This is a twofold problem. First, you can't do anything with this error. There's nothing that you can do anymore. Calling http.error isn't actually going to do anything. Second, your clients are going to get really broken JSON. It may be broken up in the middle of a key or the middle of a value, or it may be not valid JSON at all. And that can cause downstream problems for your consumers. So what you have to do instead, and what I would call production ready solution, is to render your template or your JSON into a byte slice or a bytes buffer, and then render that bytes buffer into the actual response writer itself. However, if you just allocate a bytes.buffer each time you call render template or to HTML or to JSON, you'll end up with a ton of allocations. And if your QPS exceed Go's garbage collections interval, you can actually, you can run out of memory because the GC won't clean up the old buffers if you have a lot of traffic. So what you really want to do for a production scenario is use a renderer with some type of pool. In this case, I'm using like a sync.buffer pool to reuse this allocation of a bytes.buffer. So here we're minimizing our allocations and we're using the shared buffer pool in order to minimize our memory usage as well as our allocations while also maximizing the UX and the return structures here. There is still an edge case here that you can see in the comment in the bottom where if for some reason writing to W fails, typically this is like the pipe was closed by the client. There's nothing that we can do. We've already sent the response header, so there's nothing that we can do to recover here. So we may just log an error or fire some type of metric that we could alert on later. This gets us as close to production ready as I'm aware of using the buffered HTTP renderers while minimizing allocations. The next area that really bit us was structured logging. So there are a number of popular structured logging libraries for Go, and most of them don't work well with one another. They don't share any common interfaces. If you're working on a big enough project, you have transitive dependencies, which means you have dependencies or dependencies to dependencies that have standardized on a different logging library. Getting those logging libraries to work and play nicely together is often impossible. We've written three, what I'll call logging adapters, that act as a translation layer between these different logging libraries. Because one of our transitive dependencies decided to use Logros, but our project happens to use Zap. These translators are very computationally expensive. They're doing a bunch of string allocation and parsing. We've done our best to make them efficient, but the lack of structured logging in Go is really a problem, and it's a big source of our CPU utilization. Jumping back over, let's have another pop quiz, just in case you're a little bit tired. What does the following Go code print when it's done? I'll give you a few seconds, again, since there's a delay. Feel free to post your answer A, B, C, D, E in the chat, and I will let you know what the answer is. So the answer in this case is actually CCC. And I'm not the first person to uncover this. It prints CCC because Go uses a copy of the value instead of the value itself in a range clause. It's pretty easy to see in this simplification, but in the actual code that we were working with, this happened with multiple layers of indirection and was very difficult to track down. Worse, it only happened sometimes because it was guarded with a conditional, but it's very easy to make this mistake. So what you have to do here is you either have to copy the value, so do value : equals value inside the for loop, or you have to use your original list needs to be pointers instead of the actual values themselves. Another area where we got bit, where Go is behaving as intended, but we made the wrong assumption, is with non-deterministic select statements. So let's take a use case like the following. If my system is stopped, do nothing. Otherwise, wait for a new worker or new work for up to 5 seconds. And if no work arrives after 5 seconds, return a timeout error. It seems pretty straightforward and easy to do. For example, you may do something like this. You may say, okay, well, I'm going to sit in a for loop and I'm going to select. If I'm done, I'll just return. If I get work from the worker channel, then I'll do the work. And then otherwise, after 5 seconds, I'll return a timeout error. But can anyone spot the bugs, plural, in this code? There are two. I'll give you a few seconds to post in the chat. So the first one is that we have to check done channel and only done channel before entering the main select. The reason here is that, again, going back to CPU throttling, if our CPU has been throttled for an extended time, it's possible that multiple conditions in that select statement are true. For example, more than 5 seconds could have passed and the done channel has been closed. In that case, by Go specification, who wins is undefined. We could enter either of those case statements. So to avoid that situation, we first check done channel in and of itself in isolation before entering the main select clause. This will ensure that we prioritize checking if the work has been stopped before we actually enter the main select. But this only solves half of the problem. The better way to do this is to actually bring that select inline into every case that you care about. So for example, if the done channel is closed and we get work at the same time, the order of operations of who wins is undefined by Go specification. We always want to prioritize cancellation before doing work. So anytime we get work, we have to check and make sure we haven't also been closed, and then we can continue moving along. The same is true for the timeout, though. If we time out, but are also done, we don't want to return a timeout error. We just want to return nothing. However, if we're not done, we want to return the timeout error. So This is an example of how non-deterministic select bit us. Primarily during graceful shutdown, we try to do like draining connections, and we kept getting some instances where we would gracefully terminate an instance and then still get a bunch of errors. And it was largely because of code that looked similar to this, but because we weren't handling the case that two cases could both be true at the same time and that the one that wins is undetermined, we got into some situations that were very, very difficult to debug. So with that, I'm going to stop because I throw a bunch of information at you, some of it very, very technical, and I want to make sure there's lots of times for questions. If you have questions, please post them in the chat on YouTube or in the Slack. And if you have questions that you don't feel comfortable asking in the group, feel free to ping me on Twitter. I'm at Seth Vargo. You can shoot me a DM. My DMs are open. You can also reach me at sethvargo@google.com. Thank you all so much for your time, and I'll hand it back over to our organizers.